Now let's look at one of the example for optimization using quadratic forms. So in this example, the constraint is already in the general form, so we don't need to convert or simplify it into the more simplest form. The simplest form means that x squared plus y squared equals to 1. So find the maximum and minimum values of the quadratic form z equals to 5x squared plus 5y squared plus 4xy, subject to the constraint of x squared plus y squared equals to 1. As I told you in the class, for optimization, you need to have two components. So the first is what to be optimized. And the second is the constraint. So in this case, it's quite straightforward, where we already know that this will be the constraint and this will be the equations or the aspect that you are going to optimize. So the first step is you have to express it in the matrix notation form, so that we can use the matrix or linear algebra to solve it. So z equals to 5x squared plus 5y squared plus 4xy in the form of x transpose ax. So x transpose will be in row vectors and x will be in column vectors, and the x will be the unknowns that associated with the equation here, so which is the x and y. So you have to express the matrix A here. Now if you have forgotten how to get the matrix here, just remember you write it out in this way. So this will be the x, this will be y, this will be the x, and this will be y. So this will be x, right? So this will be y. So this will be x, y, x, and this will be x, y. In another way, this will be x squared, this will be xy, and xy, and y squared. So based on the equation here, the x squared coefficient will be 5. That's why we have 5 here. And for y squared here, we have 5. That's why we have 5 here. And for xy here, because they are the same, so the 4 here has to be divided by 2. That's why you have a 2 and 2 here. So after you're done with the matrix notation, the second step is to find the eigenvalues, which is pretty straightforward, I think, because you already learned a lot of examples on how to find the eigenvalues in chapter 5. So express the matrix A, determinant of lambda I minus A equals to 0. So this is the characteristic equations that you need to use to find the eigenvalues. Then you have two eigenvalues here. So after you have the eigenvalues, definitely you have to deal with the eigenvectors. So you substitute the eigenvalues into these equations, the lambda I minus A x equals to 0. So you reduce it so that just that you get the reduced row echelon form. So we have the leading one for the x unknown without the leading one for y. So y will be the free variable. In this case, I just express this as a t free variable. And from the first equations, I'm going to express x minus y equals to 0, and x is y or equals to t. So the x vector here corresponding to xy, right? So x is t, y is t, and you factorize out the t. So this u1 will be the first basis for this matrix. And then you repeat the same step for another value of eigenvalues and continue until the last you get the second basis. So once you have found the eigenvalues and the eigenvectors, the fourth step is to normalize it. So you're going to normalize the eigenvectors. So the u1 normalization is divided by its own magnitude or norm. So in this case is the u1 is equivalent to the 1 plus 1 square. So it's a 1 square of 2. So this will be your orthonormal eigenvectors v1, and you do the same for v2. So the last one will be summarizing your maximum and minimum. So the maximum of the z will be equivalent to the larger value of the eigenvalues. So here will be 7. Minimum will be the smaller value for the eigenvalues, the 3. And of course, you want to know, this is the magnitude. At what position or what conditions that you will get the maximum. So this xy will be associated with the orthonormal eigenvectors. So in this case will be this. So v1 is from u1 and u1 is from lambda 1 equivalent to 7, and that's how you match them together. And for the minimum, you refer back to the v2 here, where v2 refer to u2 here. So u2 is the lambda 2. And what does it mean? It's actually from the spectral decomposition. Remember in the class I told you that a vector, let's say a vector x here, can be resolved into two components, right? The first is u1 and second is u2. So when you multiply this vector x with a matrix A, basically you are multiplying the u1 with the first lambda. Let's say another lambda 1, so you get a new vector here, and then you multiply another lambda with the eigenvectors here, so you get another new vector here. So summarizing these two eigenvectors will give you the end product here, so it's 3 and 0. So in this case it's the same. The maximum is the case when you multiply the eigenvectors v1 with the lambda 1 equals to 7. So this should be your maximum, and this will be your minimum when you have let's say this is the v2, so v2 multiplied with the lambda 2, so we'll give you a minimum. If you want to check your answer, if you substitute this value into the original equation, let's say z equals to 5x squared plus 5y squared plus 4xy, so you substitute the value of x and y, you end up with the same answer, z equals to 7. And if you do the same for this, you'll get z equals to 3. And that's why when you can directly use the eigenvalues for the maximum and minimum. So at the end, I have some question for you to ponder. So try to substitute the v1. Yeah, so this already told you in the sharing here.